Well, welcome back to the Physics Lounge. We're taking a look at the Level 2 Physics NCEA papers, and the last one here is electricity and electromagnetism. Oops, I always hit the wrong button there. We're going to cruise down and to the first question and have a little look on electric fields. So two parallel plates are set up 2.2 millimeters apart. Don't confuse that with meters. 2.2 millimeters apart with 15 volts between them. There's your voltage, there's your distance of separation. You do need to convert for any calculations that come up your 2.2 millimeters into meters. So you can either do that in standard form, 2.2 times 10 to the minus 3 meters, or you could just throw it into decimals if you're more comfortable with that, 2 meters. And if you're wanting to do the little count 1, 2, 3, which matches the 10 to the negative 3. So we're up to show that the electric field strength between the plates is 6.8 times 10 to the 3 volts per meter. So electric field strength, wiggly line underneath the shot's a vector field with direction and magnitude, is the voltage divided by the distance between the two plates. So the voltage you're given was 15, and the distance between the two plates in meters, because it's volts per meter, not volts per millimeter, 2.2 times 10 to the minus 3, 0.0022. You really do need to get comfortable with standard form as you move into level 3 and beyond. So quick check, does that seem about right? So what's 15 divided by 2.2? Well, 15 divided by 2 is going to be 7.5. That's a little bit less than 7.5. The 2.2 would suggest that it's going to be smaller than 7.5, which is good. And then the 3 decimal places, it's 10 to the positive 3, which is what you would expect from, anyway. It's always good to do those little checks. B, an electron at rest is released. Why do we say at rest? Has zero kinetic energy when it's at rest. It's released from the negative plate and accelerates towards the positive plate. Is that what we expect? Electron, negative charge, attracted to a positive plate. Yep. Calculate the maximum speed of the electron when it reaches the positive plate. So we want to know how much energy, how much kinetic energy has been gained by the electron. And we're going to have to do that by looking at the work done on the electron by the electric field, which is the electric field strength times the charge times the distance. So remember, this is the force times the distance, which is what you're more familiar with. E times Q gives you the force, the electric field strength times the charge, but like mg for gravity times the mass. And so E, we have the electric field strength that we just calculated or was shown above. So we have that. Charge on the electron, if it's not given here, it should be given in your resource. And if you don't know, 1.6 times 10 to the minus 19. And we know the distance or displacement between the two plates. So that's going to give us the work done. Once we know the work done, that is the same as the kinetic energy gained, half mv squared. Hopefully in your notes, in your handout, they've also given you the mass of the electron, and you know the kinetic energy now, so you can rearrange for v. So it'll be v squared equaling 2ek over m. Square root all of that, get rid of your square root there, something like that. Don't forget the units, meters per second. C, a student states that increasing the distance between the plates while keeping the voltage the same will mean that an electron released from rest at the negative plate's accelerating over a longer distance and will therefore reach a higher speed than in part B when it reaches the positive plate. Use physics principles to explain why this is incorrect. So there's a couple of approaches to this. It's a good question, actually, I quite like it. So you can go back to your calculations above and say the electric field strength is the voltage over the distance between. If your distance has increased, so if you go up here for the same voltage, you're going to go down here. Your electric field strength is going to decrease. And that has a flow-on effect to the calculation above with the work done. Work done being EQD with your electric field strength now having dropped. That will drop, that stays the same, and your distance has increased. So where So we could actually throw all of this together and see what it looks like. So work done will be volts per meter times Q times D. So what have I done? I've confused myself. So D, there is the other angle. We were talking about acceleration as well with Newton's second law, and your acceleration will be less because your electric field strength is less, so that it doesn't hold true that it accelerates at the same rate. But just carrying on with this, you can see D and D will cancel, so your work done is voltage times the Q. So the same work is done. So if the same work is done, excuse the noise of kids in the background, if the same work is done, then you're going to have the same final velocity, because the same work will mean you have the same kinetic energy gained. So regardless of any other changes, your velocity is going to end up being the same. Right, carrying on down. Oops, why is that not moving? There it goes. Quick, just read that question again to see if we've answered it correctly. So increasing the distance while keeping the voltage the same means the electron release is accelerating over long distance. So that's the part. I mean, it's true that it's accelerating over a longer distance, but the rate of acceleration will be lower because the force part F equals EQ is going to be lower with E. So it'll have a lower acceleration for the same total work done to arrive at the same speed at the end. So we'll reach a higher speed. So that's the incorrect part. Okay, hopefully that made sense. 2, state one thing that could be done to increase the maximum speed of the electron, or you could increase the voltage. If we go back up to the equations, to increase the work done, we would have to either increase the electric field, increase the charge, or increase the distance for no change in the electric field. But you can see that just increasing the distance has this, well, this is where we should really be looking. Increasing the distance has the effect of decreasing the electric field anyway. So distance is not the one that you would fiddle with. You have to fiddle with the charge, which is a fundamental constant, so you can't do that, or the voltage. So the voltage increase is pretty much the only thing you could do, unless you put the plates, would putting the plates closer together work? Well, decrease the distance, and you decrease the distance here to increase the electric field, so that's going to have the same effect, no real change. So to increase the maximum speed of the electron, it's got to be a voltage change. D, the diagram below shows the electric field between a set of parallel plates D meters apart, unknown, with V volts between them, so as a general case. Distance between the plates is now doubled and the voltage is halved. Say what happens to the strength of the electric field. Your answer should include a number. Okay, so doubling and halving tells us that it's working in that, times 2 or a quarter or whatever. If there's a squared, maybe there's an 8 in there, or 16, we'll see. So what happens to electric field? Electric field strength is voltage over distance. We've doubled the distance, so times 2 the D on the bottom, and we've halved the voltage at the top. So if we're doubling the distance by itself, that would reduce the electric field strength by half. So just let's use this with a bit of color coding. So doubling the distance would double the electric field strength, and then halving the voltage, that's dropping the voltage. Don't get confused with the fractions and the fractions. So if you decrease the voltage, you're going to decrease by half. So that's another way of saying it's half. So those two are going to cancel each other out, and you're left with the same. So it's the same. And how do you get a number from that? I think what they're trying to get it is whether it's double or half. Okay, so your answer is saying 1 times E is the new E, unless I've missed something obvious there. Comments below tell me what I might have missed if I did get it wrong. Anyway, using the same scale, draw the field lines on the diagram below to show the new electric field between the plates. Hang on a minute, I might have done something wrong here. If you are halving the voltage, oh yeah, okay, sorry, that was a bit silly actually. So I mean, you can look at it like a fraction now of the changes. Half divided by 2 is actually a quarter. So, so halving the voltage means you're going to half the electric field strength, and then dividing by 2 again because you're doubling the distance. Yep, sorry, silly mistake. Good that you can check them, eh? So you're going to have a quarter. So quarter of the electric field strength. So you've got E over 4 if you want to put it that way. All right, glad I spotted that. But yeah, again, always good to have feedback from the community, eh? That's why we learn in a community. So we can learn from each other if we make mistakes. Glad I caught that one though. Anyway, using the same scale, drawing the field lines on the diagram below to show the new electric field between the plates. So basically, we're going to get, like, if it's the same scale, 1, 2, 3. So we've got 1/4. So we're losing 1, 2, 3. We're losing a quarter of the field line. So it's like, you know, stuff all. That's even probably a bit too much. Okay. And same direction though, so arrows are pointing in the direction that a positive charge would experience a force, and that's your new electric field strength. So this one is E, and this one up down here, whoops, is E by 4. Great. That felt like a long question for the first question. Press on. Question 2, circuits. Student finds some car headlamps, 12 volts, 55 watts. Show the resistance of a single headlamp is 2.62 ohms. It's a show question, so you're probably going to use that later. But what have we got? The voltage, 12.0 volts. The wattage, which is the power rating, is 55.0. You know you've got your old Ohm's law, V equals IR. You've got your power, P equals IV. In this case, we don't have the current, so we want to combine these two equations together to go P equals V squared over R. We can substitute in V, we can substitute in P, rearrange for R, and we'll hopefully get that 2.62 ohms. The student connects 2 of these headlamps labelled A and B, you can see in the diagram below, and another lamp C, which is used to light up the number plate in the circuit below. Resistance of lamp C is 1.22 ohms, 1.22 ohms. So A and B were the 2.62, so 2.62, 2.62, and of course, being non-ohmic conductors, because temperature affects the conduction in these lamps, that's actually going to mess with it, so we're going to ignore that altogether, and we're going to just assume that when we calculate the total resistance, the assumption is they remain constant. So calculate the total resistance of the circuit, the 2 in parallel up the top, 1 over 2.62 plus 1 over 2.62, or if you're just adding it up, and then that equals 1 over the resistance in parallel, add that together, flip it up the other way, you know how it goes. Or you can look at it and know that that portion of the circuit is going to be half of that, so 1.31 ohms, and then you're going to add that 1.31 ohms to 1.22 equaling 2.53 ohms. That's the total resistance. Student connects a radio with a resistance R to the circuit. Okay, this is going to be like what happens to the current or something maybe. Use physics principles to describe the effect adding the radio would have on the brightness of lamp A. Ooh, that's a bit interesting. Assume the radio and lamps are all operating, so they're all adding a resistance to the circuit. Start by describing what effect adding the radio would have on the circuit resistance. So yeah, the first thing you have to look at is the total circuit resistance. So RT, and why? Because we want to know the flow-on effect to the total circuit current. If the total circuit current drops, that's going to be our first clue, and then we have to look at what is happening to the current in that branch down there. So if you add resistance in here, you are increasing the resistance of this part. So if you increase the resistance of that part, are you increasing or decreasing the resistance of the parallel part? You can kind of have a look by doing something like this. If it was 1 over 2, 2 plus 1 over 2, added in half, then your total 1 over 4 would be 4 would be the parallel resistance. But with if we've increased the resistance of R, down the bottom, R plus B, we might have 1 over 2 plus 1 over 4 this time. If you're not sure what that's about, maybe go back and watch the videos. I don't want to overdo it just in here. But this is the same as 2 over 4, so we'd end up with 3 over 4 for the parallel resistance, which is 4 over 3. So instead of having 4 for the resistance in parallel, you've got 4 over 3, so you decrease the resistance. Now, hopefully that made sense. Again, if I've made a mistake, let me know. I'm rushing it through there. So if you've decreased the resistance in the parallel branch, it means you've decreased the total circuit resistance, so you've increased the current flow. Decreased the, because I equals V over R, so I equals V over R. So decreasing the resistance results in an increase in the current flow. So now that we know there is an increase in current flow in the entire circuit, and what are we looking at? The brightness of lamp A. So if we've increased the current flow, we've not only increased the current flow in the total circuit, but we've increased the proportion going into circuit A. So more current is going into circuit A because you've increased the resistance in the alternate pathway. By increasing the current into circuit A, part A, you're going to have a brighter lamp. So we've talked about the circuit resistance, and we've talked about the brightness of lamp A, and we've used current flow to link all of that together. Okay, hopefully that made sense. I've got a niggling feeling I did something back to front in there. So, let me know if I've made a mistake. I'm just trying to think over it again and make sure that I haven't done that. So R and B, that's increased. So that means you're going to drive more of the current around there. That's really obvious. Does that mean that you've decreased the overall resistance of the circuit or increased it? I feel like I might have flipped that one back to front. Yeah, sometimes when you're not thinking properly, you go back to these foundational kind of ideas and just put in some numbers. So remember, this was my original, and I'm rushing through it because I'm trying to do it on a time sort of frame here. It's already getting long. Would have 1 over, that would be, no, see, I did that wrong. That should be 2 over 2. It should be 1 ohm. Whereas over here, 3 over 4, we've got now 4 over 3 when we flip that upside down, which is more than 1 ohm. That's 1.3 recurring ohms. So we've actually increased the circuit resistance because we've increased the parallel branch, increased the circuit resistance, so we've decreased the current flow in the total circuit current flow. So we've increased resistance totally in the total circuit, we've decreased the current flow, and if we've decreased the current flow, then we've means there's less overall current going into the parallel branch than there was before. But again, if we've increased the resistance in this portion, we're going to have more going into A. So are we going to have more going into A than we would have had from the change from R? That's actually gets quite tricky. I'm not sure. Unless we know what resistance R is, we might not be able to calculate that exactly. But if we stick with the numbers that I made up there, so if we'd say that's a quarter, what did we say? A quarter, so that's 2 ohms, just in my rough calculation, that was 2 ohms. And then I made this, say 4 ohms. So of the proportion, it really does depend just how much. If R is only a mild increase, yeah, no, it's more complicated than I think we'd probably get into for this video. But you can work that out, put in some sample numbers, and just see what would happen. Okay, move on. D, give at least 3 reasons why the circuit in part C would not be a good way to connect the 12-volt LED lamps in a car. Part C. One good reason is, well, it says 3 reasons. Wow. Okay, let's see what we can do. The biggest reason, it seems to me, is that when you turn the radio on and off for the radio, you're going to change the resistance in the circuit and change the brightness of the lamps. So that's going to affect turn radio on off will affect the brightness of headlights. Are they headlights or they lamps? Yeah, they're headlights. Headlamps. Not only that, you're going to have different brightness between A and B. Okay, so that's definitely going to affect what's going on there. Your radio might not operate properly either. What else is there? Is C? What is C? What is C? C is the number plate lamp. So what's going to happen to the number plate lamp when you turn the radio on? That's going to go dimmer as well. So C gets dimmer if radio is on. You want the circuit to be as stable as possible for all of the components in there. So probably the best way would be to have the radio in one branch, then a separate parallel branch for the two headlamps. This is really rough, but you get the idea hopefully. And then the number plate lamp also on a separate branch, all going to the 12 volt supply. Yeah, I don't know, there's probably a lot of ways you could phrase this, but practically speaking, these are the problems. I'm going to move on. Third, magnetic fields. A wire is pushed through a magnetic field at a constant speed of 2.70 meters per second. There's our velocity. We've got the length of the wire, L, magnetic field strength, B, and width of the magnetic field, 14.3. So usually this is your value, length of wire that you would use, and not this one for any calculations, because it's the length of the wire that crosses the magnetic field. Let's see where we go with this. Clearly mark the positive end of the wire on the diagram above. So this is a wire presumably not connected to a battery or something, so you're going to have to use a right-hand rule. I always do it by considering a positive test charge inside the wire. And if your positive charge is the direction of your thumb for your right hand, the magnetic field is coming out of the page, so you're going to have a slap downward for the positive. So this is going to be the positive end down the bottom, if I did that right. Calculate the voltage induced in the wire. E equals BVL. Remember, L is this length here. Just plug your numbers in basically. C, the wire is now stationary, connected to a circuit that contains a 3.40 ohm resistor and a 12 volt battery. Calculate the magnetic force on the wire. So F equals Bill, VIL, in this case I equals V over R, from the voltage of the supply divided by the resistance of the resistor. There is resistance in the wire and everything as well, but I think they're wanting you to assume that that is the resistance of the total of the circuit. And we don't care about that length, we want to use that length. So that length, that current calculated from I equals V over R, B is given to us. Plug the numbers in and press equals. State the direction of the magnetic force on the wire. Okay, so current flow is from positive to negative this way. Right, sorry, had a little interruption from kids and stuff. So where were we? So magnetic force on the wire. So yeah, direction of travel. We did the quantitative there to work out how much, and down below we're asking the direction. Yep. So positive flow is in that direction, so positive to negative. Our conventional current, right hand rule. The slap, if our thumb is down into the, not down into the page, just down as the page is viewed, our fingers are coming out of the page, the slap will be to the left, so the force will be to the left. Let's see if that gives us one of the options, which should be left. There we go. So it's certainly not going to be out to or into the page, because that's the direction of the magnetic field. It has to be perpendicular to the magnetic field. And yeah, anyway. D, an electron cutting the magnetic field experiences a force that makes it follow a circular path. Cool. This is like what we used to get in some of the integrated physics when that was a standard years ago. So you'd have some mechanics and stuff, but we'll see. This is maybe linking a bit too much mechanics for electricity, but still very cool. So the electron's traveling from the left into the field. That's a little bit ambiguous, but I guess it means it starts off coming from there and into the field, and it's either going to go there around that way or that way. Does it say? follows circular path, and say clockwise, anti-clockwise. Okay. Clearly mark on the diagram above the direction the electron moves around the circle. Okay, we've got to work it out. So charge on an electron's negatively charged. So there's different ways you can use right-hand rules for this. I'm just going to use one of them. If I assume that it's a positive charge, even though it's not, when it comes into the field, positive charge moving to the right, so from the left to the right, is the direction that a conventional current would travel. So with a magnetic field of my fingers coming out of the page, it's a slap down if it's a positive charge. When it's coming into the magnetic field. So that means a negative charge will experience a force upwards. So as it comes into the field from the left and experiences a force upwards, there's no way that it could go and follow this top path here. It couldn't do that, because if it experiences a force upwards, it's just going to keep going up and around that way. Because the next position of the electron in that position, travelling in, say, that direction, for a positive charge travelling in that direction, would experience a force in that direction, but it doesn't. So a negative would experience a force in that direction, it would disappear out. So it can't be going that way, so it must be going down there and around and around and around. It gets caught experiencing a force upwards, as we saw, moving towards the center, and then as it comes up in this direction, it experiences a force that way, and as it goes back in this direction, it experiences a force that way. And what a mess we have there. But basically that means it's going to be traveling around and around. It's going to come in and go around and around and around and around that way. So mark on the diagram the direction the electron moves around the circle. So we've kind of worked that out. That's meant to be an arrow. Kind of cool question. They've steered clear of the mechanics part, but it is still a little bit mechanics. Circular motion, you have an unbalanced force towards the center. Use physics principles to explain why there's a force on the electron as it cuts the magnetic field. Oh, this is probably going beyond the standard, to be honest. Good question. The way that I've always taught this is that a charged particle, I'll just use a positive test charge, as it moves through space, it opens up a magnetic field around itself. So if you imagine a wire with current flow travelling in it, the right-hand grip rule would give a electric field going around behind it and then over the front, around behind it, over the front. And that's the electric field that would open up around a positive charge moving around. So an electron, a negative charge, if it was negatively charged, would have a would be the opposite direction, basically. Now, if you take a look at it's what it amounts to then is in a permanent magnetic field. I'll just give you a kind of permanent magnetic field really roughly here. If you throw an electron moving through there and it's carrying its own electric field around it, then that magnetic field of the electron that shifts but stays with the electron as it moves is going to interact with the permanent magnetic field, called BE for electron and BP for permanent. It's going to add and subtract in different positions to create the force. So where you end up with, so on this side, this is going to be a little bit tricky to show. On this side of the electron, the magnetic field is coming out of the page because this curvy electromagnetic field around the electron is meant to be a 3D kind of picture, but it's coming out of the page on the bottom. So that's going to cancel out and you'll have like a gap of magnetic field, because the magnetic field I've drawn is showing into the page, into plus out, they're just basically going to cancel. And on the top it's going to reinforce, so they're both going, so this is going into the page here and you have a stronger magnetic field, more magnetic field lines on the top. So, and we've always said magnetic field lines want to even themselves out and be evenly apart so to experience a force going down. That's how force is produced. But this is definitely beyond the standard, I think, which is a bit unfair. Maybe they sometimes walk that fine line to try and separate the merit and excellence, or merit and high excellence and high excellence. But anyway, it's kind of cool. So does that match with what we would expect? So if this again was a positive charge moving this way, you would have a right-hand rule, you would have going into a force upwards if it was a positive charge, so that means a negative electron would experience going that direction would experience a force downwards. Yep, which works. That works nicely. You're pushing into the void of magnetic field. I think a lot of teachers do teach that way. What a tricky one. But yeah, spare diagrams, that means we've finished the paper. Generally pretty good paper. Kind of tricky last question there. Yeah, there's different ways that you could explain this as well. You could probably go back to F equals BQV and explain it as well, and just say because basically, and I mean this is just a model. Field theory is a model, a way to think about it, and it helps. It's quite a helpful model in this situation. That's why we teach it that way, to give a conceptual grounding of what's going on. But your equation is equally valid because it's just a mathematical model to say the same thing as this conceptual model. A magnetic field in a particular direction with a charge of a particular charge moving in a particular velocity, which includes direction, will experience a particular force. And it's just they're all perpendicular to each other. That's why you have the right-hand rule. The direction of motion, the direction of the magnetic field, and the direction of the force, all of them must be perpendicular to each other because that's what we observe. And this is the force quantitatively that we can work out from that. And conceptually we use the right-hand rule to show the direction of the qualitatively of the force. But yeah, I suspect the question's getting at this kind of stuff, talking about adding and subtracting magnetic field lines, but that's going beyond the standard in my opinion. Yeah, I could be wrong on that too. Talk about it in the comments, or if you've just had enough of physics for the year, since this is post-Christmas but before New Year's, you might like to just leave it as well. Be good to see what the marking schedule says at the beginning of next year when they release them. Anyway, if you found that helpful, please do share it with others who might benefit, and we'll see you in the next video at the Physics Lounge. Cheers.